Now that we have more formulas besides the basic 8 trig identities, we can use these new ones to do more complicated trig identities. Here's an example of one. I can take this sine 2 theta and replace it with 2 sine theta cosine theta. And the 2's cancel. And then the 1 over, I could change this to 1 over sine times 1 over cosine theta, which turns into cosecant theta times secant theta, which is the goal. Here's a more complicated one. I'll change the sine 2 theta into 2 sine theta cosine theta. And I have 3 options for cosine 2 theta. I'm going to choose to do the 2 cosine squared theta minus 1. That way the 1's cancel out, the 2's cancel out, and one of these cosines cancels out with one of those, and I'm left with cosine over sine, which is cotangent. Now most identities like this aren't like so important. They don't prove anything that's useful, but there is an example of this that is pretty useful. This is known as the triple angle formula for sine. And the way we prove it is by splitting up 3 theta into 2 theta plus theta, and then think of this as A and that is B. So sine A plus B is sine A cosine B plus cosine A sine B. Now this is pretty ugly looking. Sine 2 theta has to be 2 sine theta cosine theta, and this cosine theta is this one. And I have choices here. I'm going to choose to go with the 1 minus 2 sine squared theta version. And I'm doing that because I see that there's only sine thetas in the answer. So this becomes 2 sine theta cosine squared theta plus sine theta, I'm distributing, minus 2 sine cube theta. Now this cosine squared is kind of annoying there. I'm going to change it to 1 minus sine squared. Then if I distribute the 2 sine theta through, I get 2 sine theta minus 2 sine cube theta plus sine theta minus another 2 sine cube theta. Notice how the minus 2 sine theta times sine squared and the other one becomes minus 4 sine cubed. And the 2 sine theta plus the regular sine theta becomes the 3. We could similarly prove that cosine 3 theta, if I change it to cosine 2 theta plus theta, would equal this. Now those sine 3 theta and cosine 3 theta formulas, those could be proved geometrically in what I think is kind of an interesting way. It goes like this. If theta is an angle that's less than 30 degrees, and this is 1, this would be sine theta, this would be cosine theta. And if I then triple that angle, like this, make this 3 theta, and make this 1, this would be cosine 3 theta, this would be sine 3 theta. Now, this and this add up to 4 theta, so this is 180 minus 4 theta. And if I draw this this line down the middle, it's an isosceles triangle, they're both 1, so each of these is 90 minus 2 theta. This would make this 2 theta, and that 2 theta also. If I then draw this one more triangle, if this is 3 theta, alternate interior angle says this is 3 theta, but we already have 2 theta, so that's going to be theta. Now, this, in this right triangle here, the hypotenuse is 1, and the side adjacent to the 2 theta is going to be cosine 2 theta. And this is also cosine 2 theta. So together, those make 2 cosine 2 theta. That 2 cosine 2 theta is the hypotenuse of this skinny triangle. which makes the side adjacent to it 2 cosine 2 theta times cosine theta. And it makes the side opposite it 2 cosine 2 theta times sine theta. Well, if this is sine 3 theta here, it's the sum of those two things. So we can say that sine 3 theta is 2 cosine 2 theta times sine theta plus sine theta. And if I replace this cosine squared with 1 minus sine squared, I end up with the formula that we saw before. On the other hand, cosine 3 theta is over here. It's equal to this big thing, 2 cosine 2 theta cosine theta, minus this piece here, which is minus cosine theta. If I replace this cosine 2 theta with 2 cosine squared theta minus 1, it will turn into the formula that we just saw.